So this is part 2 of a proof, and we got up to putting n equals 8 into be a specific value of n, just to show how the whole situation's working once again. So we know that n factorial is equal to 2 to the 7 times some odd number, because if you look at n factorial, you can see that you can factorize out 2 to the power of 7, all the evenness out of it, and it leaves you with a bunch of odd numbers being multiplied together, 1, 3, 5, 7, and 3. So we know that. We also know that with the fraction part of things, we can write them with a common denominator, and the common denominator of 1, 2, 3, 4, 5, 6, 7, and 8 is 8 factorial. As you can see, I've written out the 1 on 1 plus 1 on 2 plus 1 on 3, etc. I've written them with the common denominator of 8 factorial, and I've written them out the long way. You can see all 8 of those fractions written out there in a big long line, and then I've multiplied by 8 factorial because we decided to get rid of those fractiony denominator parts, and we multiplied both sides of our original equation by 8 factorial. And when I multiply by 8 factorial, I get rid of the denominators, and at the same time I've factorized out the powers of 2 in each numerator. So you can see I got 2 to the power of 7 out of that first numerator, 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8, and times 1 times 3 times 5 times 3 times 7. So it's 2 to the power of 7 times some odd number. Now I could actually work out what that odd number is, but because I'm interested in a solution for n rather than 8, I'm just working it through in a more generalized way, even though I'm using a specific value here. So I've got my 8 terms factorized out, and you can see I've got 2 to the 7, 2 to the 6, 2 to the 7, 2 to the 5, 2 to the 7, 2 to the 7, 2 to the 7, and there I've got 2 to the power of 4. So if I was to pull the most evenness out of all of those, like factorize all of those 8 terms, I'd have to pull 2 to the 4 out, which I've done, and then it leaves me with the remainder, which I've written in the brackets there. You know, for the first term it was 2 to the power of 7, so now there's 2 cubed out the front of it inside the brackets, because I've factorized out 2 to the power of 4. Now what's interesting here is you'll be removing one of those even powers in front of one of those little brackets, and in this case it was the last term. So you can see, having factorized out 2 to the power of 4, the last term in my square brackets near the bottom of my screen here is 1 times 3 times 5 times 3 times 7. It's just a plain odd number, whereas all the other terms in the square brackets are being multiplied by some power of 2, so they're even numbers. So I've written that out here. I've got 2 to the 4 outside the brackets, bunch of even numbers and an odd number, which means it adds to an odd number. So it's 2 to the 4 times an odd number. Now we know that 8 factorial is 2 to the 7 times an odd number. So we can go ahead now and work out what we were trying to do. Now what were we trying to do? Well, we know that 8 factorial, the sum from k equals 1 to 8 on 1 on k, is certainly equal to 8 factorial, the sum from k equals 1 to 8 of 1 on k. That obviously, right? Now, in this case, I'm going to change 8 factorial to 2 to the power of 7 times q, some odd number q, and I'll leave this alone because that's what I'm trying to find, the summation. And on this side, I've already worked it out, and the answer from up here is that it is 2 to the 4 times p, which is an odd number. So when I just need to scroll down a bit. When I simplify that there, I can get the summation that I want by itself by dividing both sides by 2 to the power of 7 times q odd. So I get 2 to the power of 4 times p, which is an odd number, on 2 to the power of 7 times q, which is an odd number. Now we know that an odd number divided by an odd number, right, if P is bigger than Q, which I've explained before is the case, then an odd number divided by an odd number gives us an odd whole number. So I'm going to call it R odd. And 2 to the 4 on 2 to the 7 leaves you with 2 cubed, right? So we've got an odd number on the top, and we've got an even number on the bottom. Now an odd divided by an even, as we know, is going to not give you a whole number, right? So that's not equal to an integer. It's not equal to an integer. I was going to say it's not integral. So, all right, so I've shown for some specific examples, like sure, you can evaluate just by working out what that summation is for 1, 2, 3, 4, right? You can evaluate it. You can actually work it out in a more a way that leads you to a general way, like we did for n equals 5 and n equals 8. So I want to actually extend this and show that it's valid for all n bigger than or equal to 2. That summation will never actually sum to an integer. It's going to get bigger and bigger and bigger, but it's never going to actually sum to an integer like they're saying. Now, we can easily prove the truth, like I said, of the statement for n equals 2, 3, 4. So, for example, by substitution, right? If n equals 2, then the sum from k equals 1 to 2 of 1 on k equals 1 on 1 plus 1 on 2, which is just 1.5. Well, that's not an integer, is it? Right? Not an integer. All right, so that's great. What about if n equals 3? Well, we've got the sum from k equals 1 to 3 of 1 on k, which is 1 on 1 plus 1 on 2 plus 1 on 3. All right, that comes to be 1 and 5/6. Once again, it's not an integer. And what about if n equals 4? Because I've done 5, right? If n equals 4, you've got the sum from k equals 1 to 4 of 1 on k, which is 1 on 1 plus 1 on 2 plus 1 on 3 plus 1 on 4, right? That is equal to 2 and a 12th. Once again, not an integer. So, okay, I've actually shown the long way for the specific values of n, 2, 3, 4, 5, and 8. Right? We know for sure by evaluation, but we want all n, like integral n, that are bigger than or equal to 2. So we need to launch into a little bit more of a general answer, and we're going to follow the same pattern as I've done for the 5 and for the 8, but just sort of make it a little bit more general. So let's just grab a different color here. For n bigger than 5, for example, we need to first establish that that n factorial equals 2 to the y times some odd number p. Now 2 to the y, it's just some value, right? But you can pull out the most evenness out of the factorial and end up multiplying it by the rest, which is an odd number. So where p odd is some odd number, and 2 to the y is the largest power of 2, that can be factored from the n factorial. All right, well, this is clear because any factorial can have all its even part factorized, leaving only odd numbers being multiplied together, right, which gives p odd. So first of all, we need to just say that, well, that works for any. You can factorize the even part out of any factorial. And of course, all factorials you know, from 2 onwards, and we're looking at from 5, right? We're going to prove from 5 on. They've all got even parts to them. So we can definitely do that. So we know, yep, that is a given, that n factorial is 2 to the y times p, where p is some odd number and 2 to the y is the largest amount of evenness you can pull out of that. All right. So for example, e.g., 10 factorial is 1 by 2 by 3 by 4 by 5 by 6 by 7 by 8 by 9 by 10. So you can pull out 1, 2, 3, 4, 5, 6, 7, 8. You can pull out 8. It's 2 to the power of 8 is the most evenness you can get out of there, and it leaves you with 1 times 3 times 5 times 3 times 7 times and 9 times 5. It leaves you with that, which means you've got 2 to the 8 times some odd number, right? Doesn't matter what that odd number is, that's your p odd. And it doesn't matter that it's specifically 8 here, it's just some 2 to the y, where y is the biggest amount of evenness you can pull out. All right, so that's the first thing we need to establish. Then what have we got to do? We need to establish the other part of it, which is that for n bigger than 5, n factorial times k equals 1 to n of 1 on k is equal to 2 to the x times, and, well, I'll call it q, some odd number q. So, is that right? Did I use p up the top? Yeah, so I'll use q here. So we're trying to establish that. And we know that x is different to y. And we've talked through that before. But what did we do before? Well, we said this is this n factorial, k equals 1 to the n of 1 on k, is n factorial times 1 on 1 plus 1 on 2 plus 1 on 3 plus all the way up to 1 on n. Just need to scroll down a little bit here, give me some room. And we go through that same process by adding the fractions by making a common denominator, right? So here we add these fractions by making a common denominator. Okay, so this is a bit of writing, but we'll try and cut it down because we've already done it for n equals 5 and n equals 8, but we get n factorial on, all right, so we need 1, 2, 3, all the way up to times by n on 1, 2, 3, all the way up to times by n. That's 1 on 1, that's the first one. And then we need 1 times, and we miss the 2, and then 4, all the way up to n, and this is 1, 2, 3, all the way up to n, and then the next one would be 1 times 2 times, and we miss the 3, and we go all the way up to n on 1 times 2 times 3, all the way up to n, and we do this all the way through, so plus dot 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 all the way through until we get to 1 times 2 times 3 times all the way up to, and it'll be n minus 1 on 1 times 2 times 3 times all the way up to n. So all I did was write those fractions in the square brackets at the top there with a common denominator. It's not the lowest common denominator, it's a common denominator, right? Which happens to be n factorial. So if it happens to be n factorial that's on the bottom, right, you end up with this equaling to n factorial times this 1 times 2 times 3 times n plus 1 times 3 times 4 times n. Sorry, should add some dots here. Plus all the way up to 1 times 2 times 3 times n minus 1. That's all over n factorial, isn't it? And those n factorials, because there's n factorial outside the brackets, it'll cancel with the one that's underneath, and you'll end up with 1 times 2 times 3 times times n plus 1 times 3 times 4 times n plus all the way up to 1 times 2 times 3 times n minus 1. You'll just end up with that. And you'll be able to simplify that. You'll be able to factorize the highest power of 2 out of that. All right, so that's equal to 2. Now we don't exactly know what that highest power is, but there will be a highest power that you can factorize out, right? And there'll be one term that's left without, and that'll make it an odd number. So there'll always be one of the terms in the brackets that'll be odd once you've factorized it out. So you'll be able to factorize out the 2 to the x out of there, and that'll leave you with an odd number overall when you do that addition, right? You'll have some even numbers plus one odd number. It's because 2 to the x is the most evenness you can factorize out of all of those terms there. So you might explain that. You might say, now, 2 to the x is the highest power of 2 that will factorize. That will factorize. That can be factored out of, sorry, I'm just trying to scroll. That can be factored from these n terms. 1 times 2 times 3 times times n, and 1 times 3 times 4 times times n, and so on. 1 times 2 times 3 times n minus 1. So it's the highest power of 2 that can be pulled out of those. But when you pull that highest power out of 2, when we perform this factorization, all the terms will still have an even factor remaining, except one. Which means all the numbers in the brackets, all the numerators, the numbers in the brackets, are even, except one, which of course is odd. And that's why I've written above, you'll get some even numbers plus one odd number. So in the end, you'll end up with, that this sum from k equals 1 to n of 1 on k if you times it by 8 factorial, it'll be 2 to the x, and then you'll be able to times it by, now, I just want to, I keep moving, I just want to see the letter that I'm using. Up the top here, I said we want to establish that it's 2 to the x times q odd, so I'll call it q. So some number q, which is odd, right? So, and we've already explained, I think, up here what we mean by that, don't we? We need to establish that 2 to the x is the highest power of 2 that can be factored from those n terms, and we're left with an odd number q. So I might just write that where q is an odd number in case. So that's the first thing that we need to deal with, and we also need to well, we need to, have I shown that n factorial can be written? Not yet. Okay. Also, now we can write n factorial as a product of its highest power of 2 and an odd number. That's the next thing we need to establish. So n factorial is 1 times 2 times 3 times 4 times 5 times all the way up to n, right? And that's equal to 2 to the y times some odd number, and I'll write p, where p is an odd number. P is an odd number, and y is, and 2 to the y is the highest power of 2 that'll go into n factorial. All right, so we can write n factorial like that, just like up here with, where's one? There, 10 factorial is 2 to the 8 times some odd number. So here, n factorial is 2 to the y times some odd number. Now, this is importantly, this 2 to the y and the 2 to the x and how they're related, all right? So we know that n factorial equals n factorial, right? So if you multiply n factorial by something that's bigger than 1, like that summation, then it's going to be bigger than n factorial, right? But we've just said that we worked out that n factorial times that is the same as 2 to the x times this q, which is an odd number. And we're saying that's bigger than 2 to the y times p, which is an odd number. Right? Now we know that from above. So what does that mean for us? Well, if we gather together the powers of 2, we've got this q, which is the odd number, is actually bigger than 2 to the y minus x times p, which is an odd number. All right? Now, because y and x are clearly bigger than 1, like, and y is bigger than x, because 2 to the y is the most that you can factorize out of n factorial, and 2 to the x was a smaller number, as we saw from getting out of the brackets, then we know that q odd is actually bigger than p odd. It's some even number times it, all right? Q odd is bigger than p odd, since y is bigger than x and y are bigger than naught. So that helps because now we can say this. So we have that n factorial the sum is equal to n factorial the sum. So this on this side, I can just write that I've got 2 to the y times, now I've got to get the letters right, sorry, 2 to the y, sorry, that's 2 to the y times p odd. That's what n factorial is. 2 to the y times p, which is an odd number. That n factorial is timesing by the summation that we want on the left. And on the right, this all works out to be 2 to the x times some odd number q. So the summation that we are looking to evaluate is equal to 2 to the x times q odd on 2 to the y times p odd. Now, we know that q odd on p odd equals some r odd, where r is a positive odd number. I'll just call it an odd number because an odd divided by odd equals odd. Well, that's only going to work if q is bigger than p, and q is bigger than p, right? That's only going to work in that sense. But we prove that up here, q odd is bigger than p odd. So if I divide the q odd and the p odd, I get r, some number r, which is an odd number. And 2 to the x divided by 2 to the y is 2 to the x minus y. So we end up with this summation that we're after equals some odd number r on 2 to the y minus x. 2 to the y minus x, is that right? Yes, because it's on the bottom of the fraction. Yep. Okay, so that is an odd number over an even number. Right, but an odd number over an even number is not integral. All right, so therefore, for n bigger than or equal to 2, this summation is never an integer.